Throughout the history of aviation, one of the most important technological achievements has been the development of jet engines. Jet engines have experienced significant transformations throughout their history, beginning with the primitive turbojets that powered early aircraft and progressing to the complex turbofan engines that powered modern commercial and military aircraft. These modifications have served to improve performance, fuel efficiency, noise reduction, and environmental sustainability. Within the context of jet engine technology, this video traces the most significant advances, with a particular emphasis on the transition from turbojets to turbofans and beyond. 1. Early developments. The beginning of the turbojet generating process. The turbojet engine, the initial stage of development. The development of the first generation of jet engines, known as turbojets, occurred during World War II and stood out as a significant step forward in the field of aviation. Turbines are used in the operation of turbojet engines. These turbines compress air, combine it with fuel, and ignite the combination. The mixture then rapidly expands and escapes out of the nozzle, which results in the creation of thrust. The design of turbojets was rather straightforward, consisting of an air intake, a compressor, a combustion chamber, a turbine, and a nozzle. This was one of the key features of turbojets. Turbojets were a huge upgrade over piston engines at the time, enabling better speed and altitude capabilities. Fuel efficiency. At the time, turbojets were a significant improvement. Restriction. Even though turbojets were able to achieve higher speeds, they were inefficient when traveling at subsonic speeds. Additionally, they generated a significant amount of noise and heat, which made them less acceptable for use in commercial aviation. Examples: the Rolls-Royce Welland. This was the first British turbojet engine, and it was built for the Gloucester Meteor, which was the first operational jet fighter in the world. During World War II, the BMW 003 was a pioneering German turbojet engine that was utilized in the Heinkel He 162 jet fighter. The development of turbofans is the second advancement in this category. During the 1950s and 1960s, turbojets had established themselves as the standard for both military and commercial aircraft. However, it became clear that turbojets had efficiency constraints while operating at cruising speeds. This resulted in the development of turbofan engines, which offered improved fuel efficiency, decreased noise levels, and increased dependability. A turbofan engine is what exactly? The turbojet engine has evolved into a turbofan engine, which also goes by the name turbofan. There is a sizable fan located at the front of the engine, which is responsible for creating the majority of the thrust. The turbine is responsible for driving the fan. However, a significant portion of the air can circumvent the core of the engine, which results in increased fuel economy. Key features: bypass ratio. One of the defining characteristics of a turbofan is the bypass ratio, which refers to the amount of air that bypasses the core of the engine compared to the air that flows through the engine's combustion process. A larger bypass ratio leads to increased efficiency as well as a more silent operation. When compared to turbojets, the bypassed air generates more thrust without requiring the use of fuel, which results in improved fuel efficiency and a more silent operation. Noise reduction. The bypassed air also serves to reduce the noise that is created by the main engine, which is one of the reasons why turbofan engines are significantly quieter than turbojet designs. One of the earliest turbofan engines to be used on commercial aircraft, the Pratt & Whitney JT3D, was utilized by the Boeing 707 and the Douglas DC-8, among other commercial aircraft. The Rolls-Royce Conway was the first commercial turbofan engine ever built. It was utilized in aircraft such as the Boeing 707 and the Vickers Aviv C-10, among others. 3. High-bypass turbofans, the turning point in the transition to commercial aviation. In the 1970s, the commercial aviation industry saw a significant transformation as a result of the introduction of high-bypass turbofan engines. In these engines, the fans were substantially larger, which resulted in a huge increase in the amount of air that was able to bypass the engine core. Not only did this move result in more efficient engines, but it also resulted in engines that were more ecologically friendly. They produced fewer emissions. Key developments in high-bypass turbofans: more efficient fuel usage. High-bypass turbofans can generate more thrust for the same quantity of fuel, which makes them best suited for long-distance flights. Larger engines. These engines became significantly quieter as a result of the larger fans, which helped to reduce the amount of noise pollution that is connected with air travel. The increased fuel efficiency resulted in huge cost savings for airlines, while passengers benefited from flights that were quieter and more comfortable. The economic impact that this had was significant. Examples include the following. The CFM56 engine, which is a product of a partnership between General Electric and Snecma, is used to power a wide variety of commercial aircraft, such as the Boeing 737 and the Airbus A320. Because of its high bypass ratio and extremely good fuel efficiency, it quickly established the standard for contemporary turbofan engines used in commercial applications. An example of a Rolls-Royce Trent 900, one of the more contemporary high-bypass turbofans, which can be seen on the Airbus A380. By utilizing high-bypass turbofans, this engine is a prime example of the advancements that have been made in terms of power, efficiency, and noise reduction. Fourth, contemporary innovations, promoting environmentally responsible aviation and the prospects for turbofans. Jet engines continue to develop alongside the progression of aviation. Not only is there an emphasis on enhancing power and fuel efficiency in the present day, but there is also a focus on sustainability. New technologies are being created to tackle the issues that are being faced by the aviation sector, which is the subject of rising pressure to minimize its carbon footprint. Emerging trends in turbofan development, more efficient designs. The next generation of turbofan engines is emphasizing the achievement of even higher bypass ratios, the reduction of fuel consumption, and the minimization of noise. Recent developments in materials such as ceramic matrix composites have contributed to the alleviation of engine weight and the enhancement of thermal efficiency. The term hybrid electric propulsion refers to the combination of conventional turbofan technology and electric motors in hybrid engines, which helps to minimize greenhouse gas emissions and fuel consumption. To be more environmentally responsible, aircraft manufacturers are researching hybrid electric systems. Sustainable Aviation Fuel SAF. To assist in the reduction of the overall carbon emissions produced by the aviation sector, several manufacturers are currently working on engines that are configured to operate on alternative fuels, such as biofuels or synthetic fuels. Examples include the Pratt and Whitney geared Turbofan GTF, which is a type of turbofan. This particular engine is constructed with a geared fan system, which enables the fan to rotate at a slower speed than the turbine. As a consequence, the engine's efficiency is increased and its fuel consumption is decreased. The Airbus A320neo and the Embraer E-Jets E2 are two examples of aircraft that are powered by this technology. Rolls-Royce Ultrafan. Explanation. The Ultrafan is designed to achieve a significant reduction in both the amount of fuel consumed and the amount of carbon dioxide emissions by its enormous fan diameter and high bypass ratio. Rolls-Royce is also investigating the possibility of utilizing SAF with this engine to assist in meeting sustainability targets. Fifth, concluding remarks regarding the prospects of jet engines. This demand for improved performance, greater fuel efficiency, and quieter and more environmentally friendly air travel has been the driving force behind the evolution of jet engines, from turbojets to turbofans. The invention of high-bypass turbofans brought about a revolution in the commercial aviation sector. These aircraft made it feasible for airlines to operate at a lower cost, while simultaneously giving customers a flying experience that was quieter and more comfortable. At the same time that the globe is confronted with the challenge of lowering carbon emissions, the aviation industry is changing its focus toward engine technologies that are increasingly efficient and environmentally friendly. It is anticipated that the future of jet engines will be determined by improvements that value both performance and environmental responsibility. These innovations will include hybrid electric engines as well as the usage of sustainable fuels. Not only does the evolution of the jet engine reflect scientific advancement, but it also shows the resolve of the aviation industry to continue pushing the frontiers of what is possible, both in terms of performance and environmental sustainability. Don't forget to like this video, subscribe to our channel for more amazing content, and drop a comment below.
A tremendous transition is taking place in the aviation industry as a result of the emergence of new engine technologies. These technologies are being developed to solve the combined challenges of boosting performance while simultaneously decreasing environmental impact. In light of the mounting concerns that the globe is experiencing with climate change, there has never been a greater demand for jet engines that are more environmentally friendly, efficient, and powerful. The future of jet engines appears to be on the verge of undergoing a significant transformation as a result of developments such as hybrid electric propulsion, sustainable aviation fuel, SAF, and new engine designs. To what extent, however, do these emerging technologies represent the future, or are they merely speculative trends that may or may not come to fruition? Hybrid electric engines, the promise of a more environmentally friendly aviation industry. Describe the concept of hybrid electric propulsion. By combining the technology of conventional jet engines with that of electric motors, hybrid electric propulsion systems have the potential to lower the amount of fuel consumed, pollution produced, and noise levels. To achieve the goal of using electric motors to power the aircraft during specific phases of flight, particularly during takeoff and landing, the conventional turbine engine will be used to supply power for cruising. Advantages: reduced fuel consumption. Because hybrid systems make use of electricity, they can lower the amount of fossil fuel that is required during flight. Lower emissions. Electric motors do not emit any emissions while they are operating, which means that they have the potential to dramatically reduce the carbon footprint that flight leaves behind. In comparison to conventional jet engines, electric motors are far less noisy, which results in a reduction in the amount of noise pollution, particularly in the vicinity of airports. Examples of projects now under development include the following: Airbus eFan X. Airbus, in collaboration with Rolls-Royce, has been working on a prototype of a hybrid electric aircraft that is being referred to as the eFan X. One of the concept aircraft's 4 engines will be replaced with an electric motor, according to the hybrid system that will be featured in the aircraft. The Zero Avia project. To achieve zero emissions for regional flights, this business is focused on developing electric engines that are fueled by hydrogen. The middle of the 2020s is the target date for the development of aircraft that are capable of flying on hydrogen electric propulsion. The widespread use of hybrid electric propulsion confronts several hurdles, including the development of lightweight, high-capacity batteries and the infrastructure to support these systems at airports. Even though hybrid electric propulsion shows significant potential for regional flights and short-haul operations, widespread adoption faces several challenges. Sustainable aviation fuel, often known as SAF, is the key to more environmentally friendly air travel. The SAF, what is it? SAF, which stands for Sustainable Aircraft Fuel, is a biofuel that was developed primarily for use in aircraft. SAF is created from renewable sources, including plant matter, waste oils, and even carbon extracted from the air, in contrast to traditional jet fuel, which is also produced from fossil fuels. SAF may be included in jet engines that are already in operation without requiring any modifications, providing an immediate option to reduce the carbon footprint of aviation. Advantages: reduction in carbon emissions. When compared to conventional jet fuel, SAF has the potential to cut carbon emissions over its entire life cycle by as much as 80%. Compatibility with existing engines. SAF is drop-in, which means that it can be utilized in existing jet engines without the need for changes. This makes the move to SAF an easy one for airlines. Support for sustainable practices. The manufacture of SAF facilitates the conversion of organic waste into fuel, which in turn provides support to the agriculture and waste management industries. Challenges and adoption. On the other hand, despite the benefits, the widespread implementation of SAF is met with challenges. SAF is still manufactured in limited numbers, and the infrastructure necessary for large-scale manufacturing and delivery has not yet been established. When it comes to production size, SAF is still produced. Cost: SAF is much more expensive than conventional jet fuel, and its cost needs to be reduced before it can be employed on a large basis throughout the aviation sector. Support from the government. To achieve widespread adoption of SAF, police assistance is required. This support can take the form of subsidies, tax incentives, and investments in research and development. Examples: Boeing and SAF. Boeing has performed test flights using SAF combined with conventional jet fuel. Boeing has already conducted test flights. Several major airlines, such as United Airlines, Qantas, and Lufthansa, are investigating the possibility of using SAF as a realistic method to cut their emissions. The Flying V of the World Economic Forum presents, in addition to the standard air flight SAF, novel aircraft designs such as the Flying V strive to reduce the amount of fuel that is consumed. With this design, the wings and fuselage are combined into a V shape, which promises to result in significant savings on fuel use, the highest level of efficiency possible. Although hybrid electric and SAF technologies are considered to be the future of aviation fuel, conventional jet engines are also seeing substantial breakthroughs in their research and development. The development of ultra-high bypass turbofan engines is one example of such invention. While still delivering a significant amount of thrust, these engines are equipped with extraordinarily big fans that have high bypass ratios. This allows for a greater amount of air to bypass the engine core. The fact that they can improve efficiency while simultaneously lowering noise levels makes them a potentially useful technology for commercial aircraft. Advantages: fuel efficiency. Ultra-high bypass engines can generate more thrust with less fuel because of their larger fans. This makes them significantly more efficient than prior designs. The increased fan diameter also helps to lessen the noise that is produced by the engine, which contributes to an overall improvement in the experience that passengers have behind the wheel. Increased range. Because of more efficient engines, airplanes can travel greater distances without needing to refuel, which is a crucial feature for travel over long distances. Examples: Pratt & Whitney GTF geared turbofan. This engine makes use of a geared fan system, which slows down the rotational speed of the fan. As a result, the engine is more fuel efficient and produces less noise. The Airbus A320neo is one of the planes that already makes use of this technology. Rolls-Royce UltraFan. Explanation: it is anticipated that the UltraFan engine will have a reduction in fuel consumption of more than 25% in comparison to its predecessors, making it one of the most efficient turbofan engines currently under development. The function of artificial intelligence and automation. The use of artificial intelligence, AI, and machine learning is becoming increasingly prevalent in the process of designing, operating, and maintaining jet engines. The utilization of these technologies enables a more exact control over the performance of the engine, a more accurate prediction of the maintenance requirements, and an optimization of fuel usage. Advantages: predictive maintenance. Artificial intelligence can The biggest passenger plane in the world, the Airbus A380, has generated a lot of attention and conversation in the aviation sector. There have been recent advancements that have drawn interest from both industry experts and aviation fans. This thorough analysis explores the most recent developments, features, and possible future of the Airbus A380, with a special emphasis on the idea of an A380 Neo new engine option. Number 6. Overview of the Airbus A380. In what ways does the Airbus A380 reinvent efficiency and elegance in contemporary air travel? Airbus designed the four-engine, double-deck, wide-body jet aircrafts known as the A380. It is praised for its comfort, capacity, and innovations in technology. Up to 544 people in a three-class configuration may fit in the roomy cabin thanks to the aircraft's design. Its remarkable measurements are 79.1 feet in height, 238.5 feet in length, and 261.8 feet in wingspan. Number 5. Current events and conversations. Could the Airbus A380 return with modern technology to satisfy the needs of airlines today? The president of Emirates Airlines, Tim Clark, made a significant request in January 2025 for Airbus to think about bringing back the manufacture of the Airbus A380, which has long been considered the biggest and most recognizable commercial airplane in the world. A refurbished A380 would appeal to a new generation of airlines. Clark, a strong supporter of the aircraft, who are concentrating on increasing fleet efficiency and meeting the rising demand for high-capacity aircraft on important international routes. With 118 aircraft in its inventory, Emirates is the biggest A380 operator and has come to represent the success of the Super Jumbo. To handle long-haul trips, especially to and from busy hubs like Dubai International Airport, one of the busiest airports in the world for international passenger traffic, the airline has mostly depended on the A380. By effectively transporting a lot of people on a single trip, the A380 has proved to be an essential tool for Emirates, reducing traffic at these congested airports. According to Clark, there may still be a market for a redesigned A380, especially from airlines that operate in areas with large passenger volumes where capacity is essential. In order to overcome the aircraft's historical shortcomings, notably with regard to fuel economy and operational expenses, Clark's plan for a rejuvenated A380 centers on implementing state-of-the-art technology innovations. To lower the total weight of the airplane, the redesigned A380 would probably use next-generation materials such as advanced composites. In line with mounting environmental and regulatory constraints on the aviation sector, this might result in a more fuel-efficient aircraft that would assist operators in lowering carbon emissions. Clark also recommended using Rolls-Royce's UltraFan engine technology, a new generation of turbofan engines that can increase fuel economy by up to 25%. With these improvements, the A380 may become more economically and ecologically feasible for airlines trying to maximize their fleets. The A380 confronts major challenges to a possible rebirth, despite its benefits, which include roomier cabins, quieter engines, and a smoother ride. The industry's increasing preference for smaller, more fuel-efficient twin-engine aircraft, such as the Airbus A350 and Boeing 787, led Airbus to end A380 manufacturing in 2021 due to a lack of new orders. These approaches are more appealing to airlines navigating the post-pandemic environment because they provide more flexibility and reduce operating expenses. Although Clark's idea for a modified A380 is appealing, a major obstacle is the reluctance of many airline executives to make such a substantial financial commitment to an aircraft that would have unpredictable long-term demand. The idea of subscribing to big four-engine aircraft may seem less alluring as airlines place more emphasis on lowering fleet complexity and operating expenses. Furthermore, Airbus has not yet made a public statement about the prospect of resuming A380 manufacturing, and many experts think the business would be better off focusing its efforts on its more well-liked, fuel-efficient aircraft. Number 4. Airbus A380 technical specifications. What distinguishes the technical requirements of the Airbus A380 in the commercial aviation industry? The Airbus A380 is more than simply an engineering wonder. It is a representation of what can be achieved when cutting-edge design and technology are brought together. The A380 is the biggest commercial airliner in the world, and its size and scope distinguish it from all other aircraft now in use. The A380 is a massive aircraft with dimensions of 238 feet, 7 inches, 72.7 meters in length, 261 feet, 8 inches, 79.8 meters in wingspan, and 79 feet 1 inch 24.1 meters in height. These massive proportions are not only for show, they are essential to the aircraft's capacity to transport a lot of people and goods over long distances, which makes it the ideal choice for long-haul, high-demand routes. One of the most distinctive features of the A380 is its passenger capacity. It can accommodate up to 544 people in a standard 3-class layout, which leaves room for opulent first-class suites, business-class cabins, and a large economy sitting area. Because it can replace many smaller aircraft, the A380's capacity makes it perfect for routes with high demand and traffic, giving carriers efficiency and cost-effectiveness. The aircraft's capacity advantage is further highlighted by the fact that it can accommodate up to 850 people in all economy configuration. The A380's sophisticated technology and design, which guarantees seamless and effective operation, are highlighted by the fact that, despite its enormous size, it is only piloted by 2 pilots. The A380 can do amazing things in terms of performance. It can carry a lot of freight in addition to passengers because of its maximum takeoff weight MTOW, which is 1,268,000 pounds, 560,000 kilograms. Because of its 8,200 nautical mile, 15,200 kilometer maximum range, it is ideal for ultra-long-haul travel. The A380 guarantees quick, effective, and pleasant travel, with a cruising speed of Mach 0.85 and a service ceiling of 43,100 feet, 13,106 meters. The A380's reputation as the industry standard for commercial aviation is cemented by its ability to accomplish these amazing feats while providing passengers with an unparalleled degree of comfort thanks to its Rolls-Royce Trent 900 or Engine Alliance GP 7200 turbofan engines. Number 3. The A380neo's concept. Was the need for increased efficiency in the aviation sector met by the Airbus A380 new engine option? An ambitious plan to improve the already legendary A380 Super Jumbo's efficiency and competitiveness in a fast-changing aviation industry was the Airbus A380neo. Around 2015, the idea came about as a result of Airbus's realization that airlines were under more and more pressure to save expenses, cut emissions, and comply with environmental standards. The desire for aircraft that could operate with higher fuel economy while still providing substantial capacity on long-haul routes was increasing at the time, and airlines were dealing with rising fuel costs. The proposed re-engining of the A380neo was one of its main features. Originally powered by the Rolls-Royce Trent 900 and Engine Alliance GP7200 turbofan engines, the A380 would have been equipped with next-generation engines, perhaps even more sophisticated Rolls-Royce Trent engines that are particularly built to provide substantial fuel savings. By moving more air without necessarily using more fuel, these engines would provide a better bypass ratio, which translates into increased fuel economy. This would thereby lower the aircraft's fuel and carbon emissions, 2 important factors for airlines trying to reach sustainability goals. To further cut drag, the A380neo was meant to have a number of aerodynamic enhancements in addition to its engines. The wings would have been altered to contain new wingtip devices, or perhaps winglets, which are intended to lessen vortex drag brought on by the pressure difference between the wing's top and lower surfaces. Enhancing the aircraft's overall aerodynamic performance was intended to lower fuel consumption and boost overall efficiency. Other small adjustments, such improved fuselage and landing gear designs, would have also been made to the aircraft to enhance aerodynamics. Despite its potential, the A380neo idea was fraught with difficulties. The absence of significant demand for extremely big airplanes was the main barrier. In order to accommodate a broad range of long-haul routes without the enormous capacity of the A380, The aviation industry was moving towards smaller, more fuel-efficient twin-engine planes like the Airbus A350 and Boeing 787. Flexibility was becoming more and more important to airlines, and many of them tried to avoid the operational challenges of flying such big planes. Furthermore, it would have cost a lot of money to design a new engine and make the requisite aircraft changes, and Airbus had trouble obtaining enough orders to support the construction of the A380neo. A380neo, the super jumbo development eventually came to an end when Airbus said it would not pursue the A380neo. A number of reasons led to this decision, including the expensive cost of creating the A380neo, the development of smaller, more fuel-efficient aircraft, and the dwindling demand for the A380. Because of this, the A380neo is still a fascinating idea that was eventually abandoned in favor of more practical aviation industry alternatives. Even with the A380neo's cancellation, the A380 is still a famous aircraft that several carriers still fly on a few routes. However, as the aviation industry shifts to more modern, economical planes, the A380's future is still up in the air. Number 2, possible modernization and upgrades. Which major technology advancements have the potential to increase the Airbus A380's cost-effectiveness and sustainability? Even though Airbus A380 manufacturing was stopped in 2021, there is still a lot of interest in the aircraft, particularly among Emirates Airlines, the biggest super jumbo operator in the world. Emirates President Tim Clark has been a strong supporter of bringing the A380 back to life with the A380neo, an updated variant. In order to address concerns about fuel consumption and environmental effect, Clark's idea for the aircraft centers on integrating next-generation technology, namely in the form of more efficient engines. In particular, Clark has proposed that engines like Rolls-Royce's Ultrafan might be crucial in greatly increasing the fuel economy of the A380. Clark claims that these cutting-edge engines have the capacity to cut pollutants and fuel consumption by up to 25%, bringing the aircraft much closer to the aviation industry's increasing focus on sustainability. The goal to enhance the overall operating performance of the aircraft is another factor driving the drive for an A380neo. The A380neo would be able to more effectively compete with the smaller, more recent twin-engine aircraft that now dominate the market, such as the Boeing 787 and Airbus A350, by using new materials like lighter composites and improving its aerodynamics. Because of their increased fuel economy and reduced operational expenses, these aircraft have become more appealing to carriers. The A380neo can be seen as a desirable choice for airlines that want a high-capacity aircraft without compromising on environmental or financial performance, given the growing emphasis on fuel efficiency and lowering carbon footprints. The A380 is still a desirable choice for airlines operating high-density flights between important international hubs, in addition to its advantages in fuel economy. The airplane is a great option for long-haul trips because of its outstanding passenger capacity and opulent facilities. Because capacity is limited at some of the busiest airports, Emirates in particular depends on the A380. Emirates would be able to retain its competitive advantage in these areas and enhance its environmental credentials with the redesigned A380neo. The project's future is questionable, however, since Airbus has not yet made a public commitment to constructing the A380neo, despite Clark's outspoken backing. Due to the substantial operational and financial obstacles associated with redesigning an aircraft that has already seen a drop in demand, the firm has declined to comment on the viability of such an undertaking. Airbus is taking a risk with the A380neo because of the expense of re-engineering the A380 and the tiny market for ultra-large aircraft. Furthermore, it's unclear whether the A380neo will be able to generate enough orders to warrant such an expenditure, given the airline industry's growing trend towards smaller, more efficient aircraft. Despite receiving backing from industry insiders like Tim Clark, the A380neo is still just a concept that has not yet become a reality. Number 1. Airline perspectives and market dynamics. Why have airlines switched to smaller, fuel-efficient planes instead of the Airbus A380? Growing environmental concerns and the need to save operating expenses have caused the aviation sector to concentrate more on sustainability and operational efficiency in recent years. The deployment of more fuel-efficient aircraft is becoming a top priority for airlines as the global aviation industry strives to fulfill higher carbon emissions restrictions and reduce its environmental imprint. In this regard, the Airbus A380, which was previously hailed as revolutionary because of its unparalleled size and passenger capacity, is now at a turning point. The A380's four-engine design and massive size make it less fuel efficient than more recent, sleek twin-engine aircraft like the Airbus A350 and Boeing 787. Despite its remarkable capacity to carry up to 850 passengers in all economy configuration and its potential to reduce congestion at airports with high demand. Even while the A380's four engines are useful for long-haul travel and carrying large cargo, they are fundamentally less efficient than the more recent twin-engine models. Because twin-engine aircraft are lighter, have fewer parts, and need less maintenance, they may eventually use less fuel and have lower operating costs. Modern twin-engine aircraft engines, like the GEnx engine on the Boeing 787 or the Rolls-Royce Trent XWB, also provide lower emissions and more fuel economy. One of the main causes of the current preference for the A350 and 787 by many airlines is this move toward twin-engine aircraft. There is increasing interest in figuring out how to make the A380 more competitive in this shifting market as airlines continue to place a higher priority on fuel economy and a smaller environmental effect. One possible remedy is the idea of an A380neo, which would include next-generation engines like the Rolls-Royce UltraFan and other aerodynamic improvements. By lowering fuel consumption and emissions by up to 25%, these upgrades might bring the A380 closer to contemporary sustainability targets. Concerns about running expenses and the environment would be addressed by increasing fuel economy via the use of lighter materials and design modifications to enhance aerodynamics. Future airline purchase choices may be influenced by the A380neo's capacity to satisfy these requirements. The A380neo may be a desirable alternative for airlines looking to satisfy environmental goals while maintaining capacity, especially on routes where there is a strong passenger demand. Yet big aircraft are needed due to airport congestion. Airbus may provide a competitive substitute for smaller twin-engine aircraft by updating the A380 and improving its fuel economy, enabling the A380 to maintain its position as a mainstay for long-haul, high-capacity flights in the future. The initiative's success, however, will rely on how economically the required technology developments can be applied without sacrificing the aircraft's overall functionality and attractiveness. In conclusion, because of its size, capacity, and passenger comfort, the Airbus A380 is still a major aircraft in the aviation sector. The continuous interest in updating the aircraft to satisfy present market needs is shown by recent talks over a possible A380neo. Although no formal plans have been revealed, airlines and industry experts are nonetheless interested in the idea of a redesigned A380. A 380's future will be influenced by a number of variables, including market demand, environmental concerns, and technical developments. Like, share, and subscribe for more awesome content. Hit the notification bell and join our community. Your support means the world. Thanks for watching. The aviation business is always adapting to provide efficient, contemporary, and environmentally friendly aircraft as technology advances. Large airplane manufacturers are fighting for consumers' trust. Does this present an opportunity for Airbus while Boeing remains mired in the muck created by the 737 MAX? The entire industry was taken aback when the European manufacturer recently unveiled the concept for a next-generation airplane. What can we expect from this new aircraft? Why is everyone talking about it? Today's program will tell us. Let's get started. Since entering the market, Airbus has launched a variety of aircraft models to fit every need, from the small A220 to the huge Airbus A380. They can please every consumer with their diversity, from wide-body to narrow-body, from single-aisle to twin-aisle, and from short-range to long-range. Airbus recently stated that it is trying to continue improving the fuel efficiency of its aircraft and is in negotiations with engine producer Rolls-Royce about its next narrow-body aircraft. To investigate technology for the upcoming generation of narrow jets, Rolls-Royce has said that it is creating a scaled-down version of its UltraFan prototype engine. We are now progressing towards a demonstrator on what I call small engines in narrow body, CEO Tuan Aran Bilek told reporters at the Farnborough Air Show, adding that the business was discussing the technology initiative with aircraft manufacturers. At the same Paris Air Show a year ago, he informed reporters that Rolls had enough room for expansion in its large engine sector to survive without future alliances in the narrow-body market. We are constantly pushing for new generation technologies in materials and engines. It is essential to stay that one technological leap ahead. We have the latest generation technology available today. Julie Kitcher, the Chief Sustainability Officer of Airbus, told the media during the Farnborough International Air Show 2024 that for every new generation of aircraft, we increase fuel efficiency and therefore reduce fuel emissions by around 25%. Airbus's CEO has made it plain that the aircraft builder is striving for major improvements in fuel efficiency, including the capacity to run engines on 100% SAF, which would reduce emissions. At the same time, we are working on hydrogen technology to have a hydrogen-powered aircraft. The two will complement each other. To research hydrogen-powered aircraft and propulsion systems, Airbus has created the Zero Initiative, which includes 4 aircraft prototypes: a turbofan, a turboprop, a blended wing body, BWB for short, and an electric idea. By 2035, Airbus hopes to have the first commercial aircraft fueled by hydrogen on the market. The Zero project is investigating different setups and technologies to accomplish that, in addition to setting up the ecosystem that will generate and deliver hydrogen. Each of the 4 Zero-E variants will run on hydrogen. As it advances toward its goal of launching a commercial airplane fueled by hydrogen, the manufacturer is hitting several testing and technological benchmarks. Many of these center on the advancement of propulsion, whether it is via direct hydrogen combustion or hybrid hydrogen-electric fuel cells. To create hydrogen fuel cell stacks as the central component of an electric propulsion system, Airbus has even established a joint venture with suppliers. Demonstrators for the company's hydrogen combustion and fuel cell propulsion technologies have been launched. Additionally, it has established specialized development facilities to work on tanks and cryogenic fuel systems in France, the UK, Germany, and Spain. Leading the way in testing these technologies, which are essential to launching a commercial aircraft fueled by hydrogen, is Airbus's A380 MSN-1 testbed. Future materials need to be stronger, lighter, and more affordable than ever before to realize cutting-edge aeronautical designs. With an emphasis on digitalization, multifunctionality, and environmental effects, Airbus is now investigating the possibilities of future materials. The utilization of a variety of materials to promote the development of cutting-edge aeronautical concepts has been pioneered by the aerospace industry during the past few decades. These consist of coatings, ceramics, metals, composites, and other associated procedures. Today, sustainability is the main emphasis of Airbus's future materials development. First, in aircraft products, total environmental impact can be improved by reducing its footprint across its worldwide life cycle through resource usage and material waste disposal optimization. The next feature is multifunctionality. Incorporating several uses into a material can facilitate predictive maintenance and minimize manufacturing downtime. Additionally, it will enhance mission performance and make advanced concepts possible. Another notable divergence from conventional airplane design is Airbus's revolutionary wing design. Its fuselage and wings are combined into a single continuous shape, a feature known as blended wing body configuration. Aerodynamic advantages are provided by this design. The BWB design lowers drag, which increases range and fuel efficiency. Within the aircraft structure, hydrogen fuel can be distributed and stored more effectively thanks to the BWB design. Additionally, the Zero Wing design integrates a hybrid electric propulsion system that combines a conventional jet engine with a hydrogen fuel cell-powered electric motor. The wing's ability to hold hydrogen tanks guarantees a secure and effective way to store this extremely combustible fuel. Airbus hopes to develop a more efficient and sustainable airplane that may drastically lessen aviation's environmental effects by fusing these cutting-edge features. A crucial element of this enormous project is the BWB wing design. Thank you very much if you have stayed with us this far. To ensure you don't miss any of the most recent aviation news, please subscribe to our channel. If you could like, comment, and share your thoughts about this video, it would be greatly appreciated. Many thanks. A 352,000 Airbus creating an entirely new airplane is quite challenging and can take over 10 years. Therefore, we must also take into account the less hazardous choice of creating a new airplane based on an already existing model that is currently on the market. Yes, the stretched form of the A350-2000 is what I mean. When it was first presented, industry insiders believed that its adoption would address capacity difficulties. Talk about the A350 extension emerged in the mid-2010s when the A350 began to display its strength. This 2000 variant, with its expanded fuselage from the present A350-1000, was projected to be a major hit. It would have 40 to 50 more seats than the 1000 because it would be around 4 meters longer. In addition to being a difference that some consumers could seek, this would place its capacity into a more competitive range. Additionally, the additional weight would not be greater than the A350-1000's maximum weight. Therefore, if Airbus were to move forward with such a development, it might potentially be powered by the same Rolls-Royce XWB engines. There is still significant disagreement regarding its capabilities, even though it was initially meant to take the place of the A380 when the Super Jumbo's production run came to an end. The first is the size difference. The A380 is the biggest commercial aircraft ever constructed, with a high-density seating arrangement that can accommodate over 800 passengers. The A350-2000 would probably be far smaller than the Super Jumbo jet, even if Airbus were to develop it. The market niche comes next. The King of the Skies was mainly built for extremely long-haul flights between important hubs. It is perfect for linking densely populated cities because of its large capacity. Even in its enlarged form, the A350 could not be as popular on these specific routes. But if it is created, the A350-2000 might be able to serve a different market niche. It might be marketed as a more adaptable and efficient substitute for the A380, with a somewhat lower capacity but appropriate for longer journeys. Because of this, it might be appealing to airlines that need a big plane, but don't need the A380's extreme capacity. In the end, several variables such as consumer demand, technological viability, and financial concerns will affect the A350-2000's development. Airbus doesn't seem to be actively working on such a project at this time. To put it briefly, Airbus is leading the way in aviation innovation by investigating both novel aircraft ideas and possible improvements to current models. The corporation leads the market thanks to its emphasis on new technology, including hydrogen engines, fuel efficiency, and sustainability. The new Airbus planes have a bright future. What do you think will happen to them? Please let us know by leaving a comment below. Created for the UltraFan engine program, the superalloy RR1073 can tolerate temperatures up to 50 Kelvin higher than the present RR1000 alloy, providing a longer and more consistent service life. To significantly reduce operating temperatures and improve engine longevity and performance, Rolls-Royce has also redesigned the high-pressure turbine blade cooling system, which better reroutes airflow. These cutting-edge turbine discs are already being produced, and they will soon be included in the XWB-84 and XWB-97 engines. Upgrades include better secondary air systems, tighter sealing between turbine stages, increased turbine cooling, and improved aerodynamics are also included in the EP version. The purpose of these adjustments is to minimize inefficiencies and further optimize turbine blade clearance. In the meantime, Rolls-Royce is working to improve the XWB-97 engine's durability, especially for use in hot and sandy conditions. High-pressure turbine blades will be equipped with improved casting layers to reduce metal wear from high temperatures, and a new sand-resistant coating is being developed to protect engine components. By the end of the year, these improvements should be implemented, establishing new standards for engine efficiency and resilience. Saving money isn't the sole reason for this improvement. Even a slight increase in fuel efficiency becomes crucial since the aviation sector is under growing pressure to lower carbon emissions. Governments, environmental organizations, and travelers who are growing more concerned about the effects on the environment are all scrutinizing airlines. In addition to helping to satisfy these legal requirements, having a fleet with higher fuel efficiency offers a major competitive edge in the marketplace. However, there are many obstacles in the way of putting these enhancements into practice. For good reason, the aviation industry is known for being risk-averse. Failure can have serious repercussions that impact both financial stability and safety. The reason stems from the fierce competition in the aviation sector, where even a small performance improvement can result in airlines saving millions of dollars. One of the biggest operational costs for airlines is gasoline, and even a 1% increase in fuel economy can be the difference between profit and loss, particularly on lengthy flights. A lengthy journey from London to Singapore, which usually uses about 70,000 liters of fuel, can help put this into perspective. 700 liters of gasoline are saved every flight with a 1% reduction in fuel use. The savings for a single route quickly reach millions of dollars when multiplied by hundreds of flights annually. Imagine the financial impact of these savings when applied to an airline's whole fleet of A350 flying on many international routes. The real test for these enhanced engines will come when they are widely deployed for commercial use. If successful, the enhancements might solidify the A350's status as the most efficient long-haul aircraft in its class, allowing it to maintain a competitive edge for years to come. Airlines using the upgraded A350 may experience considerable improvements in profitability, giving them a competitive advantage in an industry where profit margins are notoriously low. But what happens if, despite all measures, unforeseen concerns develop once these engines achieve general commercial use? The aviation industry still remembers the reliability challenges Rolls-Royce encountered with its Trent 1000 engines on the Boeing 787 Dreamliner. Aircraft groundings, severe airline disruptions, and large financial losses resulted from these issues, costing Rolls-Royce billions of dollars and decreasing its market position. Similar issues with the improved engines might cause flight cancellations, groundings, and huge financial losses for A350 airlines. Airbus faces significant risk. If performance or reliability difficulties damage its reputation and lead to order cancellations or moves to competitors, it could lose its wide-body market dominance. A severe setback would hurt Rolls-Royce. The company invested heavily in these changes, financially and reputationally. A major engine failure could threaten its commercial aviation survival. However, these high risks drive aviation innovation. Failure risks are equal to success benefits. Do you see any more issues with this engine? Rolls-Royce and Airbus would have a huge edge if they could keep their promises. More fuel-efficient aircraft might save airlines a lot of money over time, affecting fleet decisions. How does Airbus upgrade affect Boeing? Boeing faces a big challenge modernizing the A350 engines, especially for long-haul aircraft. Boeing's latest move may nullify the 787 Dreamliner's operational and fuel economy. A 1% fuel economy boost on the A350 may not sound like much, but in aviation, even small numbers can influence airlines' purchasing decisions. Boeing must work hard to match and exceed these advances to regain its edge. Boeing's recent history complicates this endeavor. Boeing's reputation suffered after the 737 MAX issues questioned its quality control and inspection methods. Boeing must prove it can produce competitive goods going ahead and rebuild customer trust after these losses. Boeing may lose its long-haul market share if Airbus's A350 upgrade, especially its Trent XWB engine cooperation with Rolls-Royce, attracts more customers. Not keeping up with these advances may hurt Boeing's market position. As airlines increase their demands on Airbus and Boeing to function efficiently, their competition will intensify. Boeing must fulfill Airbus's new A350 engine upgrade criterion. As airlines cut expenses and improve the traveler experience, long-haul passengers may see better comfort in service. However, new technology, environmental restrictions, and economic developments may affect how airlines and manufacturers handle future issues in the aviation business. As was mentioned, Boeing is significantly impacted by this. We'd love to hear your thoughts on what Boeing should do, but we leave that open. Please share your thoughts by leaving a comment below. The aviation sector, known for its technical advances, often suffers major failures that interrupt operations and cost money. Engine defects have grounded fleets, cost airlines money to repair, and damaged engine manufacturers' reputations. This video explores contemporary aviation's most significant engine issues and their far-reaching effects. Number 6. Pratt & Whitney's Geared Turbofan (GTF) engines. Could a single flaw in the metal potentially bring down the entire aviation industry? The General Transportation Fuel (GTF) engines manufactured by Pratt & Whitney, in particular the PW1100G, were developed with the intention of revolutionizing the industry by enhancing fuel economy and reducing noise pollution. However, airlines worldwide have faced difficulties in implementing these regulations. Vibrations and groundings. The PW1000G engines that were used to power Airbus A320neo aircraft were experiencing excessive vibrations by the year 2018, and they typically occurred within 1,000 flight hours. Because of the severity of these problems, which were most noticeable during the ascent stages, regular inspections and premature replacements were required. In the first year of service, Lufthansa reported that its A320neos were grounded for an average of 254 days, with engine-related issues being responsible for 78% of the downtime that occurred. Metal contamination recall. Due to the presence of contaminated powdered metal that was used during the manufacturing process, Pratt & Whitney initiated a recall for 1,200 PW1000G engines in the month of July 2023. This defect could result in cracks in the components of the engine, which would pose a significant threat to safety. By September 2023, the recall was extended to include all 3,000 engines that were working, and it was estimated that inspections would take between 250 and 300 days for each engine. It is anticipated that the recall will cause an average of 350 aircraft to be grounded around the world until the year 2026, with the peak impact expected to occur in the beginning of 2024. According to estimates, Pratt & Whitney and its partners are facing a financial burden of between $6 and $7 billion, primarily for the purpose of compensating customers. Go First bankruptcy. In March of 2023, the Indian airline Go First, which had a fleet of Airbus A320neos, ceased operations and proceeded to file for bankruptcy. The airline attributed its financial collapse to a number of factors, the most important of which were the reliability issues with its PW1000G engines and the absence of spare engines. Pratt & Whitney refuted these assertions, indicating that more widespread operational inefficiencies caused the airline's problems. Number 5. Rolls-Royce Trent 1000 engine problems. What causes the flagship engines manufactured by Rolls-Royce to fail in some of the most advanced aircraft in the world? Ever since it was first introduced, the Trent 1000 engine, which is the engine that powers the Boeing 787 Dreamliner, has been plagued by durability issues. Due to the difficulties that Rolls-Royce has been experiencing with this engine, airlines that depend on the Dreamliner for long-haul flights have been affected in a domino fashion. Fan blade degradation. The Trent 1000's fan blades and cooling systems have proven prone to rapid deterioration, resulting in frequent maintenance needs. This has resulted in grounded airplanes and decreased operating efficiency for airlines. Impact on British Airways. British Airways BA has encountered substantial interruptions owing to Trent 1000 engine difficulties. The airline has been numerous Dreamliners have forced the airline to ground, resulting in the cancellation of hundreds of flights and impacting tens of thousands of customers. Despite spending over £1 billion on durability enhancements, BA remains doubtful about the long-term dependability of the engines. Number 4. The wider impact on airlines. How are engine problems costing airlines millions, and may your trip be next? Engine defects don't simply burden manufacturers, they have cascading repercussions on airlines' operations, finances, and customer pleasure. Below are some prominent examples. Wizz Air's profit decline. European low-cost airline Wizz Air reported a 21.3% decline in profitability in the summer of 2024, mostly owing to parked aircraft awaiting engine checks. By September 2024, 41 of its planes were out of service, with the airline anticipating 40 to 45 grounded aircraft over the following 18 months. Despite the losses, Wizz Air is extending the life of older jets, leasing new aircraft, and maintaining a profit prediction of 350 to 450 million euros for the fiscal year. Operational challenges. There is a potential for decreased capacity and higher operating expenses for airlines that have fleets that are dependent on troublesome engines. Among these provisions are the leasing of new aircraft, the extension of maintenance schedules for older aircraft, and the management of compensation claims from passengers who were adversely impacted. Number 3. Impact on aircraft manufacturers. What are the factors that prevent Airbus and Boeing from satisfying the demand in the rapidly expanding aviation market? For airplane manufacturers such as Airbus and Boeing, who depend on timely engine deliveries to achieve production objectives, the consequences of engine faults extend throughout the whole aircraft manufacturing industry. Airbus. There are delays in delivery. Unfortunately, Airbus has experienced considerable delays in the delivery of aircraft as a result of problems in the supply chain and shortages of engines. The business was only able to produce 766 aircraft in 2024, which was far below the revised objective of 770. One of the reasons for the delays is that there were problems with CFM, which is another engine provider. Airbus has set a goal of delivering between 825 and 850 aircraft by 2025, and it intends to raise production to 900 aircraft per year by 2027. Supply chain. As a result of the difficulties that engine manufacturers such as Pratt and Whitney and Rolls-Royce have been experiencing, the supply chain for aerospace has been subjected to extra pressure. Other factors that have contributed to the delays include a lack of components and a rise in the demand for maintenance parts. Number 2. Financial implications. Under what circumstances are engine problems turning airlines that were previously prospering into financial disasters? Flaws in engines have far-reaching financial ramifications, affecting not just manufacturers, but also airlines and even lessors. Manufacturer costs. Pratt and Whitney is facing billions of dollars in compensation and inspection expenses, while Rolls-Royce's financial resources have reached their limits due to the company's investment in durability upgrades for the Trent 1000. Airline losses. A number of airlines, including Go First, have filed for bankruptcy, while others, such as Wizz Air, have recorded significant decreases in their profits. Leasing new aircraft and extending maintenance schedules are two examples of items that contribute to increased operating expenses. Passenger compensation. Because grounded fleets result in flight cancellations and delays, airlines are required to pay customers who have been harmed by these events, which further strains their financial resources. Number 1. Lessons and future outlook. Are the jet engines of today too technologically sophisticated to be reliable? Recurring problems with contemporary jet engines bring to light the difficulties associated with striking a balance between innovation and dependability. Despite engine design innovations aiming to enhance efficiency and reduce emissions, dependability difficulties may overshadow these advantages. Key takeaways. When it comes to preventing faults in production, rigorous testing and quality control are absolutely necessary. There is an absolute need for engine makers, airlines, and regulators to work together in order to reduce the negative effects of faults. A reduction in dependence on a single manufacturer and a distribution of operational risks may be achieved by the diversification of engine suppliers. Looking ahead, learning from these issues is necessary for the aviation sector in order to prevent expensive errors from being repeated. While engine manufacturers are making investments in cutting-edge materials and design enhancements, airlines are implementing fleet management systems that are more resilient. However, since it is anticipated that the demand for air travel throughout the world will expand, the pressure that is placed on engine makers to offer products that are dependable and efficient will only increase. In conclusion, modern airplane engine difficulties highlight the delicate balance between innovation and reliability. Despite their efficiency benefits, the Pratt & Whitney GTF and Rolls-Royce Trent 1000 have proved challenging to implement. These issues impede airline operations and expose aircraft supply chain flaws. To ensure a safer future for aviation travelers, the industry must prioritize longevity and quality. Like, share, and subscribe for more.